Good day, I'm Dr. T. Welcome to my office. Today I'd like to talk about energy and a little bit more about momentum. And you know what? Our favorite cannon, or at least my favorite cannon, is going up over there. When we're talking about this one, so obviously we've got the cannon, we're putting a force on that, but that force isn't just coming out of nowhere. So we are taking some gunpowder, putting it in there, and that is going to be chemical potential energy. We can get energy out of that gunpowder by getting enough heat to kick it over the activation energy, and then boom, the energy is coming out whether you want it to or not. Now, this is going to exert a force on our cannon and our cannonball. Now, as it's doing this, we already talked a little bit about momentum. The momentum is conserved, so the cannonball goes one way, its mass and velocity is going to be the same as the cannon's mass and velocity, but in this case, the cannon's got a lot more mass, and the cannonball's got a lot more velocity. Now, when we do that, when we add that momentum, we call that impulse. So impulse is kind of the change in momentum, sometimes described as force times time. Basically, how long did you push the cannonball? Hence why a longer barrel gets you a little bit more oomph for your cannonball. But there is another thing that we can look at, and that is going to be energy. How much of that energy do we take from that gunpowder and do we put into the cannon or the cannonball? Truthfully, not much. Most of these systems are very inefficient. A lot of the energy is dispersed as heat, which is random motion of atoms, instead of this nice orderly motion of either the cannonball going one way or the cannon going the other. Now, energy, when it comes to energy of motion, we call this kinetic energy. So we've changed the energy from this chemical potential to kinetic energy, which is energy of motion. And in doing so, that is what we refer to as work. Work is very much the energy version of impulse. So what impulse is to momentum, work is to energy. So we are adding energy, or we're changing the energy. We're taking it from one thing and moving it to another thing, and thus we're doing work on it. With respect to kinetic energy, that is going to be how hard you pushed it, so force, because this is going to look really similar, times how far you pushed it. So how far along the barrel did you push it? And that's going to describe how much kinetic energy you're going to add. Okay, so we've got kinetic energy. Our cannonball is moving, it's going to be traveling, and in this case, I'm going to pretend this cannon is pointing straight up, which one, you would never do that to a cannon. You don't fire them straight up. And two, obviously it's not. But also that there's no air in this situation. Once again, once you start factoring in air resistance, it's the real world, but it's also a pain. So we're going to make those assumptions. So the cannonball is coming out. It's now got a bunch of kinetic energy that it has acquired. Now, kinetic energy is going to be a function of mass and velocity, similar to momentum, but it is more a function of velocity. So it's going to be 1/2 the mass times the velocity squared. So something that's moving faster is going to have noticeably more kinetic energy, and thus could impart that to something else. So if I look at my cannon, the cannon's going to be moving backwards, but at a much slower rate. So most of the energy that didn't go into heat goes into the cannonball. And that's why if you look at a cannon, they're really big compared to the size of the cannonball. And of course, they usually have giant feet or big ropes to keep them from going too far back. That's due to the momentum. Okay, so now the cannonball has got this kinetic energy. It's traveling. But there's still a force acting on it. So there's a force that could act on it over distance. Oh no, we've got work. And that force is gravity. So what this is going to be doing, once again, we're pretending there's no air. What this is going to be doing is it's going to be converting our kinetic energy into gravitational potential energy. So the higher up something goes, then the more energy you're going to take to put it that high up. Likewise, the more energy it's going to be from it falling back towards the Earth, or towards whatever is causing your gravity, which, we're on Earth, so we'll call it Earth. So in doing this, so now, as it's traveling up, it's losing velocity. As it's losing velocity, it's losing kinetic energy, but that's not going away. Energy, like momentum, is conserved. you don't simply get rid of it. You can transfer it from one thing to another or change its form. So unlike momentum, energy is a scalar quantity. Momentum is vector, it's going in a particular direction. Energy is just how much you have, and you can change its form back and forth to different types. So with my kinetic energy, as I'm going up, as gravity is pulling on it, it's slowing down. That energy isn't just going away, that's becoming gravitational potential energy. I could get that energy back. I could use that to do work by letting it fall down. So as it's going to go up, it's going to eventually reach its top. It's going to have its vertical motion stop, and if the cannon was truly pointed straight up, it would stop. Now all of its kinetic energy has been converted into gravitational potential energy. The reason why I keep saying gravitational potential energy is because it can come in more than one form, like the gunpowder. That was chemical potential energy. Okay, so once it's up there, you've got gravitational potential energy. And this is going to be a function of how high you are, how heavy you are, and how much gravity there is. Now, of course, on Earth, the acceleration due to gravity is 9.8 meters per second. But hey, if you're on the moon, it's a fraction of that. So it just depends on how much gravity is actually pulling on you, as far as how much your gravitational potential energy goes. But we're on Earth, so we can basically, just that's a constant. It's mass and how high up you are. Okay, so now at this point, you can then do work with that. So that can be converted back to, by simply letting the cannonball fall, back to kinetic energy. And so then it's going to be, as it's falling, converting the gravitational potential energy into kinetic energy. It's going to speed up and it's going to go faster and faster. If there was no air, then the point where the cannonball was level with where it's left the cannon, what we call the muzzle, then at that point it'd be going just as fast. Now with air, obviously it's going to be going slower because it will have experienced air resistance the whole path. But if you're in a vacuum, it goes just as fast. Okay, so yeah. Now, of course, depending on what you're doing, you could use that gravitational potential energy to do work on something else. So if you think like a trebuchet, that has a big old massive thing of probably rocks or lead on one end, and then that goes down and the other end goes up really quickly. It's like a gigantic slingshot. Or you could imagine, a dam with lots and lots of water behind it, and you can store up that water and use its weight to flow through turbines, and you basically make a giant gravity battery. And there are actually smaller gravity batteries. So with that said, have a wonderful day.